All right, it's lesson 25, which means we are well into the second half of Calculus 1. We are well on our way toward the big ideas we approach throughout the course. This is a little speed bump along the way. This is Newton's method. Newton's method is a numerical way to approximate roots of functions whose roots may be hard to find. But remember, the big theme in Calc 1 is that everything basically becomes lines. Every function is basically its tangent line in a small interval. And so we're going to take advantage of that fact looking at Newton's method. So here's the basic idea. You've got some function. You've got some function looks like so. Call this thing f of x, and you're looking for an approximation for this root right here. And maybe you don't know where the root is. Maybe you just know that it's near some place. And so what you do is you pick some place near where you think the root is, and you say, hey, the function is basically its tangent line. And if that's the case, then I can use the tangent line to approximate the function, figure out where the tangent line has a root. This thing is our next guess for where the root is. So we guessed something here, and then this becomes our next guess for where the root is. And you say, well, okay, what's the tangent line at this point? Well, the tangent line at this point goes like this, and it hits the x-axis there, and that spot is our next guess for where the root is. So this goes back to the idea of linearizations. In linearizations, you have f of a plus f prime of a times x minus a. In this case, that's our a value. That's the place we begin. But we don't just want a linearization. We want zeros from the linearization, which means we want the y value to be 0. That's a number. That's a number. That's a number. That's the thing we're looking for. That's the thing we're looking for. When we find that, that's going to be our next approximation. This thing is going to turn out to be x1. So how do we get that? Well, we kick this over to the other side. Again, the thing we're looking for is this. So how do we get that? Well, you divide by f prime of x0. And again, the thing that we're looking for is this x1. So how do we get that? Well, we add the x sub 0 to both sides. And so x1 is x0 minus f of x0 over f prime of x0. Now, there isn't anything special about using x0 and x1, because once we have x1, we drop down to the function, we draw the tangent line, we're looking for x2, then these all become x1s, and this becomes an x2. So in general, the next approximation we're looking for is the previous approximation minus the function there over the derivative there. This is the thing commonly referred to as Newton's method for finding a root. I will illustrate. Let y equal x squared minus 5 and x0 equal 2. This almost makes sense. We know that there's a root here that's just bigger than 2, so 2 is an obvious place to guess. So how does this go? Well, x1 is x0 minus f of x0 over f prime of x0. So x1 is 2 minus f of 2 over f prime of 2. F of 2, that's -1. F prime of 2, we didn't even find f prime of 2 yet. 2x? That makes sense. So f prime of 2, that's 4. So this number is 2.25. This number is 2.25. So then we go, well, x2, that's x1 minus f of x1 over f prime of x1. So that's 2.25 minus f of 2.25 over f prime of 2.25. So that's 2.25 minus f of 2.25, that's, I think, 0.0625 over f prime of 2.25, that's 4.5, and you get some number, and it's about 2.236-ish. And we can keep doing this and doing this and doing this. The more we do it, the better the approximation is. So the root is approximately 2.236. We could do it again. We could get better approximations by continuing Newton's method. Take the 2.236, run this process again. We could, we won't, but we could. I'll show one other. Let's estimate where y equals 3 minus x squared meets y equals radical x. So you've got this function, you've got this function, you've got this function. Where is that point? Well, it's about at 1 maybe. I mean, that's not a bad place to start. The problem is Newton's method requires one function, and it requires looking for a root. So you're like trying to figure out where this meets that. Well, you need a single function, and the single function that I want to use is that one, because that's the thing that you would put in y1 if you were looking for a root. And while we're at it, we'll take its derivative. So we will let x naught equal 1 and see where that goes. So our first approximation is x0 minus f of x0 over f prime of x0. That's 1 minus f of 1 over f prime of 1. And this actually happens to be 1.4. And so then we try again, x1 minus f of x1 over f prime of x1, that's 1.4 minus f of 1.4, which is like this weird, awful decimal number, over f prime of 1.4, and this is this equally weird decimal number, and that's 1.356, and we can get better approximations than that if we keep going, but 2 iterations seems like it does okay. Okay, so that's all I wanted to say about Newton's method. You should be generally familiar with how it works. I will see you when we gather in class.